Hello. Good day, everyone. Can everyone confirm if you can hear me clearly? Is everyone hearing me clearly? Yeah, I need someone to confirm. If you can hear me clearly, I need someone to talk so that I'll be able to be sure, when you are talking, maybe you want to ask question, I'll be able to know whether my network is working. Can somebody confirm if you can hear me clearly?
Yes.
Okay, thank you so much. Want to welcome everyone to my lecture today. I find myself a little bit under the weather this morning, and of course, I plan to have emergency doctor appointment today because I'm a little bit under the weather. So, and that's why today's lecture is going to be conducted remotely. And I want to welcome you to my lecture today. We started chapter 12 on Monday, and of course, we're going to continue from where we stopped. Okay, but today, the focus is going to be on numerical summaries of the relationship between two quantitative variables. Okay, the other time I introduced you to analysis of quantitative variables. And of course, I've walked you through the graphical way of doing that. Okay, so what we want to do now is actually, the numerical way. Is there a way we can actually make use of formula, to figure out um, correlation or regression? Okay, so that's going to be the focus today. So in the outline, I'm going to differentiate again the difference between correlation and regression analysis. And of course, there's going to be a lot of illustrative example to that regard. Okay, so we started using this example from our class on Monday, where we're trying to investigate relationship or association between Olympic winning times for the 200-meter dash and the year in which the Olympics took place. And of course, looking at the data set, we actually want to consider Olympic that was aired after 1900. Okay, the Olympic that was aired after 1900 was the one between 1908 and 1996. And of course, I actually said something the other time, 1996 Olympic was actually, was aired in Atlanta, Georgia. Okay, so, and of course, the next is going to be held in Los Angeles. I think you know that. But let me tell you this, the 1908 Olympic was held in the United Kingdom, London, United Kingdom, and that was held in April, between April 27 to 31st of October 1908. Okay, so the focus is just, we just want to excuse me, we just want to investigate relationship between the numbers of years after 1900 and of course the Olympic winning times for 200-meter dash. The data set can actually, this is a link to the data set, and of course, these are the bivariate data, okay, year against time. Okay, year, 8 year actually means I'm talking about 1908. And of course, 12 means I'm talking about 1912. And 20 means I'm talking about 1920. Okay, so the data go all the way to 1996. Okay, so I said something the other time, if you want to investigate relationship between two quantitative variables, you need to first identify what is the response, what is the explanatory variable. And of course, the response variable, is actually the 200 meter, the time for the 200-meter dash. Okay, that's going to be the response variable. The explanatory variable is actually going to be the year. Okay, the Olympic was held. Of course, before you're going to have the dash, before you're going to have the 200-meter dash, of course, Olympics actually need to be held. So before going to numerical way, the very first point of call is actually to go graphical way. So how do we construct a scatter plot in R? Okay, so if I have a diagrammatical plotting of the response variable against the explanatory variable, this is the code. Okay, I need you to pay attention right now. So this is the code. Okay, we're actually gonna call that a scatter plot. Okay, so the very first variable that is gonna come is gonna be the explanatory variable, followed by the response variable, and of course, this is just the label for S, and this is the label for Y. And of course, when you take a look at this guy, PCH equal to 16 is actually saying arrow should return a solid dot. Okay, arrow should return a solid dot. And of course, I'm actually gonna show you right now, okay, what the output is gonna be in terms of the plot. This is what I have here. As you can see right now, we have in the uh, excuse me, we have in the vertical axis, we have the dash time. And in the horizontal axis, we have the numbers of years past 1900. And this is a scatter plot. And of course, I told you in class on Monday, the direction of this plot is negative, and it's actually strong because majority of the point are very close to the line of best fit that I call a straight line. Okay, and that was why I said strong, negative, linear relationship. Okay. And of course, the interpretation for that, okay, for negative relationship, the interpretation for that is that, okay, the 200-meter times have been improving over time, okay, because the time for the 200-meter dash and the years, they are actually move apart. They are inversely related. And that's an improvement, when it comes to reducing time, because I know every athlete wants to reduce the times, okay? But when you take a look at this, okay, I mentioned strong, okay, using the correlation, using the scatter plot, there's, it may create, there may be a kind of confusion in interpreting that for strong or weak or maybe moderate, and that is the reason why we need a numerical approach. So with the numerical summary now, okay, the numerical summary now, okay, we actually gonna have a way to compute the strength of the linear relationship. Okay, and the only way to go by that, it means we actually want to quantify the relationship. We actually want to have a particular value. Okay, and for us to be able to do that, we're going to assume that we have, of course, a set of data set. We have data set. Okay, X. Okay, maybe I'm talking about um the year the Olympic was held. Okay, the number of time Olympic has been held. Okay, then you look at the numbers of the 200-meter, the lowest, the fastest 200-meter time. Okay, now you're going to see we are x1 up to xn, right? We also got y1 up to yn because they are expected to be two paired of sample size n. If I got 10 observation in X, I'm also going to have 10 observation in Y. Okay, so for us to be able to have numerical value for that. So since we have some data set, we have data set for S, we got a set of data set for Y. We're going to find the mean of S. We're going to find the standard deviation of S. We're also going to find the mean of Y. We're also going to find the standard deviation of Y. So that's what you're seeing here. So which means, and of course in this class, you've already been taught on how to get the mean and the standard deviation from data set. Now, the formula for correlation now, if you actually want to compute that manually, okay, if you want to compute that manually, okay, this is the formula here. But if you take a look at this formula right now, okay, it's like I got X, okay, I got Y, right? Okay, I find the mean of X, okay, I find the standard deviation of X, okay, I find the mean of Y, okay, I find the standard deviation of Y, okay, and after that, I'm also going to get the Z, okay, Z for S. So the Z for S, the Z score for S, okay, the Z score for X is actually, the S, a particular S, minus the mean of S, okay, minus the mean of S, okay, divided by the standard deviation of S, okay. I'm also going to do the same. I want to get the Z-score for Y, okay. The Z-score for Y, okay, is also going to be, okay, Y minus the Y bar, okay, divided by the standard deviation of Y, okay. And what am I going to do next? Okay, so what am I going to do? Somebody said, can you please give a reminder on how to find the X bar, Y bar? Of course, how to find the X bar is adding the mean, adding the values here together, divide by the number. That's how to find the mean. Okay, you add the number up and divide by the number of observation. Okay, so then the standard deviation, of course, we have the formula that I gave. So here, just like what you said, if I want to find the mean is summation of X, sum of X divided by N. The standard deviation now for X, okay, the standard deviation for X is going to be summation X minus X bar. You can use your calculator, okay? Some of them are inbuilt in the calculator. You can use your R, okay? Divided by that. Take a look at that. So this is how to find the mean. This is how to find the standard deviation. You find the square root, okay? So you can use your calculator for that. You can also use R for that. Of course, if I want to find the mean using R, mean into the data, into X. That will give me the mean of X. If I want to find the standard deviation of X, that's going to be SD. If I want to do R, SD into X. Okay, so I think you've already done all of that. Now, after getting that, the next thing is, okay, thank you too. After getting that, okay, the next thing is you go to another column where you multiply the two Z-score. It's going to be ZS, okay, multiplied by ZY. And you're going to divide by N minus 1. Okay, so definitely you're going to have for across observation. Then you sum them up. When you sum them up, you have your correlation R. When you sum them up, you're actually going to have your correlation R. Okay, so that is a manual way, to figure it out. If you have your correlation Y, I want to show you something now. What are the possible values the correlation can take? And now let me tell you this. Correlation is denoted as R. We use R to denote correlation. Okay. Now let's go to the property now of R, the property of correlation. Okay, the values of R does not change if you reverse the role of X and Y. Maybe you misinterpreted maybe S to be response variable, and you misinterpreted Y to be explanatory variable. If you compute your correlation, it's not going to change. It's still going to remain the same. The value of correlation is going to remain the same. What am I talking about? Okay, if you take a look at this, if this guy is here and this guy is also here, that's what it means. It's still going to be the same. The R is going to be the same because A multiplied by B. Okay, so what am I trying to say? What I'm trying to say is this. Give me 1 second. Okay, ZS multiplied by ZY is the same as ZY multiplied by ZS. Okay, if you switch the values of your correlation, it's still going to be the same. Excuse me, it's still going to be the same. I just wanted to take note of that. Okay, another thing we're going to take note in the property is when let's say you're working with a unit, maybe you were working with pounds, X and Y are both in pounds, and you calculate your correlation. If you convert X and Y into kilograms and you calculate the correlation, you're still going to have the same value. You're still going to have the same value of correlation. Okay? But that requires they have to be in the same unit. Okay? And let me tell you this. Correlation only apply to linear relationship. Linear. If the relationship is curved or non-linear, correlation does not apply. And let me also say this. Okay? Correlation is not resistant to outliers, which means it is sensitive to outliers. Why is correlation sensitive to outlier? Because of the fact that in correlation we make use of the means. Mean of S, mean of Y, standard deviation of S, standard deviation of Y. And let me tell you this, the mean is actually sensitive to outlier. So when mean is sensitive to outlier, correlation will also be sensitive to outlier. Okay, I just wanted to take note of that. So that was why we said it's not resistant to outliers. Okay, so if you make use of the formula here, you compute your correlation, okay, or whether you use a software, you so we compute your correlation. The correlation is going to lie between -1 and 1. If your correlation is less than 1, you are wrong. If your correlation is greater than 1, you are very wrong. Okay, so the reasonable correlation value should be in this interval, -1 to 1. I told you the other time, correlation measures the strength and the direction of the relationship between two quantitative variables. And let me tell you this, okay? If you take a look at what I have right now, you're actually going to see that when R is greater than 0, okay, when R is greater than 0, when you have a positive R, that's a positive association. Uh, excuse me. So positive association actually imply positive relationship. If R is less than 0, you have a negative, that's a negative association. When your correlation equal to 0, it means there is no association, there is no linear relationship, or you can also conclude that the two variables are uncorrelated. So uncorrelated means whatever that happened to S, whether S increases or S decreases, Y is unaffected. I'm going to say that again. When R equal to zero, when correlation equal to zero, when correlation between two variables is equal to zero, it means when one variable increases or decreases, the other variable is unaffected. Okay, that means there's no correlation. Talking about strength right now. Okay, talking about strength right now. Okay, so when R is much more zero, very close to zero, we're gonna call that a weak. Okay, when R is very close to +1 or -1, that's gonna be called a strong. Okay, if it is negative, if it's very close to -1, that's gonna be a strong negative linear relationship. If it is very close to +1, there's gonna be a strong positive linear relationship. Okay, and I say if R equal to 1 or R equal to -1, only if all points fall exactly on a straight line. Let me tell you this. Well, if I take you back here, okay, if I'm gonna draw a straight line right here, okay, if I'm gonna draw a straight line, let me see if I draw a rough or straight line, you're actually gonna see it is not all the point on a straight line. If all the point land on the straight line, that is the situation where R can be equal to, like here now, R is going to be -1. That's a perfect negative relationship. We don't have a perfect negative. We don't have a perfect positive as well. Because of the fact that there's always going to be a distance between model and reality. Okay? We're never going to have a perfect straight line. And that's why this is called a scatter plot. Just wanted to take note of that. Okay, now what I'm trying to give in this picture now is when you use your R, when you use that formula to calculate R and you got this is the corresponding scatter plot. I need you to take a look at this guy and this guy. Okay, they are both strong, right? But they are in different direction. And can you see that? Then if you take a look at -0.6 and +0.6, this is the corresponding scatter plots. They are also in the same, I mean, they are in different direction with with the same magnitude, but different direction. If you take a look at -0.3 and zero point 0.3, you're also gonna see the same, they actually have the same magnitude, but they are in different direction. I want you to take note of that. Okay, how do you compute correlation in R? Okay, if you want to compute correlation in R, okay, when we go back to the example on the winning time for 200-meter dash in Olympic, and the year the Olympic was actually held. Don't forget the winning time is going to be the lowest time ever in that particular Olympics. If I want to do that in R, if I have my data set and I actually want to compute correlation in R, if I don't want to use this particular formula here, because this particular formula here is going to take forever, okay? And of course, that's why we need, to use software. And in this class, we're using R software. If I have my data set, okay, I got my data set on year and time, of course. If I write COR, it's going to give me the correlation value. Okay, I told you the other time, if I switch time for year, take a look at this, it's also going to give me the same results. If you take a look at this now to 3 decimal, okay, to 3 decimal, of course, I'm actually going to say is this, and how can we interpret this guy now? Okay, this is a strong, okay, because why do I call it strong? It's very close to -1. So a strong negative linear association between time and year. If you take a look at the numerical value that we have here, you're actually going to see this is disagree with the plot here, with the graphical summary. Take a look at that. They agree. Okay, now let me tell you this. Um, correlation, the significance of correlation is that correlation can tell us the strength and the direction of the relationship between two quantitative variables. But you know what? Correlation cannot actually handle prediction. I'm going to say that again. If I have information about Olympic, if I know the year Olympic was actually held, correlation cannot be used to predict what the winning time for the 200-meter dash is going to be. I'm going to say that again. Correlation does not undo prediction. Correlation is only going to tell us whether the relationship is positive or negative, or whether the relationship is weak, strong, or moderate. Okay, but correlation cannot answer the question when we actually want to make a prediction. Okay, for instance, the next Olympic is going to be held in Los Angeles in the United States. Before that Olympic, if we want to make the available data set to make a prediction, how can we make if we want to make a prediction ahead, like what the winning time in 200 meter is going to be in Los Angeles in 2020? I don't know, maybe it's 2026 or 2030 or maybe in 2030, okay, when the Olympic is going to be held. Of course, the correlation cannot answer that question. And what is going to answer the question is regression. Because of that, I want to welcome you to regression analysis. We actually use regression, if we want to answer a question that has to do with predicting one variable from the other using the relationship they got. And that was why I call this numerical summaries for predicting the response from the explanatory variable. And we're going to do that using a linear equation. Okay, the linear equation, the approach is what we call least square regression. We call that least square regression, and I want to welcome you to regression analysis. I want to welcome you to regression analysis. Okay, the weakness of correlation is that correlation cannot actually be used to make a prediction, or what correlation does is actually to have the measure of the relationship in terms of strength and direction. Now, if I want to talk about prediction now, I'm going to make use of regression line. But if I want to make use of my regression line, I need to properly identify my response variable and my explanatory variable. The response variable is denoted as y, okay? The explanatory variable is denoted as x. Now the question now, if I'm able to formulate a regression line, okay, given the value of x, I actually want to figure out the values of y. Before moving forward, I want somebody to confirm again if you are still hearing me clearly. Is everyone still hearing me clearly?
Yes.
Thank you so much. And in case if you want to ask a question, if you need some kind of clarification, somebody said, can you please give a reminder on how to find X bar? Oh, I think I've already answered that. Okay, the person said, thank you. Okay, now if I actually want to use regression line, I need a regression equation. Okay, I need a regression equation. I need all of you to pay attention now. You've seen something like this in high school. We're breaking it, and we actually bringing it back again. That's a regression line. Okay, it is not this. If you write this, you are wrong. Please pay attention. And as pay attention, if you actually write this, you are wrong. Okay, what is the difference between, I said this guy, this is wrong, but this is right. Okay, if you take a look at the Y here, the Y here is having a cap. The Y cap actually means the predicted values of y given s. Okay, but the original y is the actual values of y. Okay, maybe the y here is the winning time for 200-meter dash in in Paris. Okay, the last Olympic was held in Paris, France. Okay, we already know that. That's the original y. That's an actual values of y. But the y cap is the predicted. Maybe before it happened, we make a prediction. That's a y cap. So y cap is different from y. Okay, and of course, when you take a look at s, of course, your s is the explanatory variable. Now, the main parameters of interest in regression line is actually a and b. Okay, a without s is what we call the intercept, which is the values of y cap when s equal to 0. This is an intercept, and b is the slope. Okay, you can see that b is the slope. Okay, you've done something like this in high school, and that's why I normally want you to commend the efforts of the teachers in elementary school, in middle school, and in the high school. They've done a great job. I want to believe they've introduced you to something like this before. Okay, now we're actually gonna benefit, from that foundational knowledge that you acquire from them. Now, when if you before you can make a prediction of y, you need to first compute your a and b. But I'm trying to tell you now, the a and b can actually be, you can obtain that from the scatter plot. The moment you draw your scatter plot and you draw the line of best fit, if you take a look at this line now, you're actually going to see that doesn't start from origin. Okay, situation where, let's say for instance, I got this guy now. If let's say if the line start from here, then your a, it will be equal to 0. Intercept equal to 0 when the line start from the origin. But right now, the line doesn't start from the origin. My a is going to be this particular point, which is the intercept. Now, if you want to find the slope, of course, you're actually going to draw. Okay, you're going to actually use the approach that you use in the high school to find the slope, which is going to be the change in, the expected change in y per unit change in s. So from the straight line, you're actually going to draw something like this. Take a look at that. That way, that you're actually going to do y2 minus y1, okay, divided by x2, okay, minus x1, okay. Of course, here now, this is your x1, right? Take a look at that. Okay, so this is your x2, okay? Okay, from the triangular descent, and this guy here is actually your y1, okay? And this guy here is actually your y2. And of course, with that, by the time you do that, you're actually gonna get your slope b. Okay, I want you to take note of that. Okay, so after getting your slope, we're trying to get a and b using the graphical approach right now. Okay, we also have a formula to do that using a numerical approach. What I'm working on now is using the graphical approach. Now let's look at when we get your b. There's a relationship between correlation R and the slope B. Don't forget, we talk about slope when we're talking about regression line. Okay? R for correlation. Let me tell you this. Both correlation and slope, they are in the same direction. Please take notes. It's going to be part of the final. When slope is positive, correlation is also going to be positive. When correlation is positive, the slope is also going to be positive. When correlation equal to 0, when correlation is less than 0, that is, when correlation is negative, slope is also going to be negative all the time. Slope, all the time. Slope and correlation, they're always going to have the same direction. They're going to be in the same direction. Don't forget that. Okay? Now, let's say I already have my regression line. If I have my regression line, okay, maybe you're giving your A, maybe you have A to be equal to 2, and you have B to be equal to that, and they want you to write down the formula. Don't forget, the regression line is Y cap. Don't forget, when you write Y, always put a cap on Y. Okay, the cap on Y actually means predicted. Y, okay? Now you know what I'm going to do now. I'm actually going to plug in 2 here. I'm going to plug in negative 1 over 4, and that is going to give me that. You see that? That's a regression line. Do you know the moment I plug in my A, and which is my intercept, and I plug in slope, which is B, I can make a prediction where they give you values of S. I can predict Y. Take a look at that right now. Yeah. A further question said, predict Y for S equal to 100. Oh my God. This is more or less like evaluation in high school. Okay. You remember in high school or middle school where they give you a function of S. Okay. They give you a function of S. Okay. Do you know why this guy here is more or less a function of S? Y is the same thing as a function of S. So here S equal to 100 means they actually wanted to find f of 100. That's what they mean. Okay? That's an evaluation. And that is the reason why you have to give kudos. You have to commend the effort of the teachers in the middle school and the high school and the elementary school. They are doing a very great job. So when I plug in 100 now, okay, plugging in 100 now, I'm actually going to evaluate that and I'm actually going to get these results. Okay, I can also predict when S equal to 4, plug in 4, the same way we handle that, that's going to give you 1. What we're doing here, we're making a prediction. We need a regression line to make a prediction. Is there anyone who want to ask question based on what I've explained so far? Is there anyone? If you really understand what I've explained so far, I need you to comment yes, or you say yes, or you give me a thumbs up if you really understand what I've explained so far. Okay, I can see a lot of yeses in the chat. Okay, if you don't understand, ask a question. I'm actually going to re-explain that. All these, they're going to be in the final exam. Don't forget that they're going to be in the final exam. Okay, so actually want to move right now. I want to move right now. Actually want to move right now. Okay, this is being recorded, and of course, I've been sharing my recordings. Okay. Now, uh, you know, I'm also going to walk you through an approach. How do we get A and B? Of course, when you sketch this kind of plot which is the diagrammatical plotting of y against s, of course I think I just show you how to get your A and B. But let me tell you this, I told you the other time we got two types of y. Okay, we got a y cap. The y cap actually means the predicted y. This is predicted y. Okay, that's a predicted values of y. Okay, the predicted values of y. Okay, let me tell you this, whenever we make a prediction, there's always going to be an error. Okay, we call that prediction error. Okay, and the prediction error is called residual. Residual is a difference between what your model predicts and what happened in reality. What happened in reality is actual y. If you take a look at the actual y, that is the actual response. Okay, this is the actual response. Okay, maybe this is the 200, the time for 200-meter, winning 200-meter dash in the Paris Olympic, and maybe before Paris Olympic, maybe immediately after the Tokyo Olympic hosted in Japan, we predicted what that value is going to be y cap. And the gap, the difference between what happened, the difference between the actual response and the predicted response is actually called residual. Okay, it's actually called residual. Okay, what we normally want to do, okay, before our prediction can make sense, okay, we actually need to have, uh, we need to minimize the gap. The gap has to be, the residual has to be very small. Okay, when the residual is small, we celebrate. Okay, when the residual is very small, then it means, our predicted response is very close to the actual response. Okay, I just wanted to take note of that, and that's exactly what I'm trying to show here. Okay, so, and how are you going to get the y cap? Don't forget, you're actually going to make use of the regression line. You need to have your A, you need to have your B, and given any values of S, you're actually going to have a y cap. Okay, and let me also tell you this. The residual is y minus y cap. The actual minus predicted. It shouldn't be the other way around. I'm going to say that again. It shouldn't be the other way around. Okay, what I mean, we cannot switch the order. Okay, for instance, if I ask you to find residual and you do this, if you write y cap minus y, okay, this is wrong. This is not correct. Okay, it has to be y minus y cap. Okay, this is right. Please don't forget that. Want to get residual. So there's going to be y minus y cap and not y cap minus y. I need you to pay attention to that. Okay, but you know what situation where residual equal to zero? Oh my God, when residual equal to zero, it means we're hitting the nail on the head. Hitting the nail on the head actually means what we predict, what our model predicts is exactly what happened. Okay, that's what I mean when residual equal to zero. Okay, what of in a situation where residual is less than zero? Okay, if the residual is less than zero means the residual is negative, then it means um your predicted value is too high. How do I know that? Don't forget, it is y minus y cap. Okay, if this guy is less than zero, then it means this particular value is high. The predicted value is high. It's higher than the actual value. Okay, that is the only condition. And and if it is positive, then it means the predicted value is too low. Okay, I just want you to take note of that. Okay, now you know how to interpret residual. You know what residual means. And when residual equal to zero, when residual equal to zero is having exact characterization of reality. Okay, residual less than zero, okay, means the residual is negative. And if there's going to be a gap between what you predict and what happened in reality, okay, it's either the difference is negative or positive. Okay, that's what I mean here. Now, the next thing that I want to talk about, how do we choose the A and B? You know, in the regression line, we need A and B. A is the intercept, B is the slope. How do we choose that? We don't just choose A and B arbitrarily. We want to choose A and B to make sure that the residuals are very, very small. What do I mean by residual? The distance between what our model predicts and what happened in reality. So we want to choose A and B in such a way our residual is very, very small. Okay? And that's exactly what we mean. So that we don't want to have a situation where we're going to over predict a true value or we're going to under predict. Okay, we want to run away from overestimation and underestimation. And that's the reason why we're going to make sure when we want to choose our A and B, the residuals have to be small. Okay, I'm actually going to walk you through that approach. Now, I'm going to start from here in the next class. Okay, that very approach is what we call residual sum of square. Okay, how do we choose A and B? Okay, without using the formula, without using the graphical means, how do we choose A and B in such a way to minimize the sum of square, the residual? Okay, I'm actually going to, that is where I'm going to start in my next class. I'm stopping